Hi everyone, my name is Yulei Bai. Now I work at Guangdong University of Technology. Today my report title is Internal Stream Measurement with High Resolution and Signal-to-Noise Ratio using Phase Contrast Optical Coherence Tomography. The report includes 4 parts. 1. Background. As is well known, a composition material is produced for 2 or more constituent materials. Compared to the traditional metal material, the composition material has notably physical properties, such as high strength, thermostability, and low density. Due to these mechanical advantages, the composition material can be designed as the stringed components, which are widely used in spaceflight area. For example, the wing, the enclosure of energy, and so on. With the widely used of the composition material, the tiny cracks, layer defects may appear under the effect of loading. These defects can cause the mechanical failure, resulting in terrible disasters. To prevent disasters caused by the damaged composition material, it is very important to detect the tiny defects. Currently, there are 2 kinds of defect detecting methods. One is the profile measurement, another is the stream measurement. The profile measurement regards to the reconstruction of material structure, and therefore the shape of defects can be obtained. This technique's feature is very simple, but has low sensitivity. The stream measurement regards to estimation of material stream fields, and the tiny defects can be visualized in terms of the principle of stress concentration. This technique has an advantage of very high sensitivity. So, compared to the profile measurement, we prefer to use the stream measurement because it has a very high sensitivity and it can use to detect the tiny defects. At this moment, the popular stream measurement methods include the electronic sparkle interferometry, computed tomography combined with the digital value correlation. Unfortunately, the electrical sparkle interferometry is only suitable for measuring the material surface. Although the CT can measure the internal stream distributions, yet the sensitivity is pretty low. Overall, these methods cannot simultaneously meet the requirements of high precision and the internal measurement, which is very limited for the mechanics application. Phase contrast optical coherence tomography can enable the internal stream measurements with high precision and high sensitivity. Therefore, the PCOCT is a promising tool to quantify the mechanical properties inside the composition material. This is the experiment step of PCOCT built by our own research group. This is the stream measurement results of polymer materials measured by the self-rebuilt PCOCT. Although the PCOCT is a promising tool to quantify the mechanical property, there are 2 problems which limit its application. The problem A is the poor axial resolution. The axial resolution is limited by the laser band wide, resulting in portable 10 micrometers. This index makes the PCOCT hardly recognize the internal structure of composition material. The reason for the poor axial resolution is the convolution of the window function. The problem B is the low signal-to-noise ratio for the estimated stream distributions. Consequently, the PCOCD cannot completely obtain the mechanical information of the composition material. The reason for the low signal-to-noise ratio is that the refracted intensity from the layers inside the composition material is too low. Therefore, the strong noise exists on the fixed maps. 2. The proposed method. The OCT signal formed by the M-layer composition material can be modeled as a superposition of the multiple sinusoidal functions. In the sinusoidal signal, the frequency and the phase can be used to reflect the structure and the deformation of a certain layer inside the composition material. Here is the sinusoidal frequency, and it can be used to obtain the material's structure. That is the optical path difference. The sinusoidal phase can be used to risk-contrast the actual displacement fields. That is the delta D. We proposed a new idea of asset resolution improvement. That is, the asset resolution improvement can be treated as the single channel blind separation of multiple sinusoidal signals. Here is the example. Supposing the material has 3 layers. Each layer corresponds to the sinusoidal signal with single frequency. Now the CCT captured the OCT intensity, which is the superposition of 3 layers sinusoidal signals. So the asset resolution improvement is to separate the sinusoidal signals with close frequencies. Based on this idea, we established the linear model of the OCT signal. After that, we import a sparse automation to reconstruct the OCT amplitude and phase. To minimize the effect of sparkle noise, we further proposed a total least square method to optimize the OCT spectra. Finally, a high resolution of these maps can be obtained. To improve the high signal-to-noise ratio of the stream fields, we propose a convolution neutral network to estimate the strain distributions. The network generalization depends on the training stage. Here we give 3 steps for the training process. The first step is use a computer to generate the random numbers, and then extrapolate the numbers by importing the Lagrange function. The step 2 is according to the physical resolution. Then the deep gradients of the phase maps can be estimated by performing the numerical difference along the vertical axis. Final step is by using the generated phase maps. The input data corresponding to the web phase can be evaluated using the web2pi function in the MATLAB. Then the various phase noise is added to the web phase. Here is the training architecture. 3. Experiment. We first conduct the computer simulation for testing the assay resolution improvement. First, we simulated 2-layer composition material. The 2-layer composition material has 4 mature sparkle surfaces, which is S1, S2, S3, and S4. The distance between the front surface, middle layers, and the back surface are 5 micrometers, 50 micrometers, and 30 micrometers respectively. Then we simulated the mechanical loading and obtained the out-of-plane displacement distributions for the S1, S2, S3, and S4. Then we simulated the lens imaging. Noted that the front surface is focused. Finally, we simulated the laser output. The band wire is here, and we can calculate the original SL resolution is 12 micrometers. D is the sparkle, and D is the before deformation, and D is the after deformation. And D is the result estimated by the Fourier transform. And we can see that the spectrum of layers S1 and S2 and S2 are missing and cause the poor reconstruction of the displacement fields. Here is our proposed method's results, and we can see all the displacement fields and the reference results are close to the preset values, and especially the missing spectra are restored and show that the high SL resolution are obtained. D is the error analysis for the proposed method, and we can calculate that the errors are around 50 nanometers. And D is the real experiment for testifying the strain estimation by using the two different methods. And we can see the second line is the popular methods caused by the vector methods, and the last line is our proposed CNN, and we can see the CNN has a very high signal to noise ratio. For conclusion, we have two conclusions. One, the blind separation model for the PCOCT signal was proposed. In this model, the deep resolution is the ability to blindly separate sinusoidal signals with close frequency, and we complete the separation in the wave number domain by the optimization of a matrix equation. The simulation showed that the deep resolution was refined nearly 3 times. 2. The proposed deep learning-based approach can successfully estimate the strain field distributions in very complex deformed situations with high signal-to-noise ratio. Besides, the method can reconstruct the strain fields even in a large deformed regions, thus expanding the dynamic range of PCOCT. Here, the above is all my presentation. Thank you for listening.